far we have seen the wave nature of light. We discussed that we called light a wave because it showed diffraction, it showed interference, but we will also discuss now about the particle nature of light. The next topic of discussion is particle nature of light. It was believed that light is a wave, but then there were some experiments which could not be explained if you use the wave nature of light. You needed to reinterpret your understanding about the light to be able to explain those experiments. We will discuss two of those experiments. They are very famous experiments. The first experiment that the wave nature of light could not explain is known as the black body radiation. We will come to this black body part little later. Let us talk about radiation first. Whenever we see an object with a color, for example, this pen that you see, this is blue in color. Why do I see it as blue? The light, the white light in this room, they fall on this pen. The material that this pen is made up of, it has this property that it absorbs all the light except for the light that corresponds to blue color. The wavelength that corresponds to blue color, this particular wavelength gets reflected. Since it gets reflected, it reaches my eyes or it reaches your eyes, and therefore, you perceive it as blue. So, we see a color of this color of a body because that is the color that it reflects. You also might have seen if you put an iron rod in a furnace, you see that as you increase the temperature of the furnace, the iron rod will get hotter and hotter. To begin with, it would appear, when it becomes very hot, it would appear slightly dull red, somewhat maroon color, and then you increase the temperature further, it becomes bright red. Slowly it will become whitish in color, and then eventually it becomes blue. Why do we see different colors at different temperatures? It so happens that when you heat a body, it starts radiating, and it starts radiating lights of all wavelengths. But what happens is that at one temperature, at every temperature, it is actually radiating all wavelengths. But at different temperature, the intensity of one particular wavelength becomes higher. For example, when we are heating this iron rod, at initial temperatures, the intensity of the red light was higher than compared to the intensity of any other light. That is why we saw this iron rod as red. As we increase the temperature of the furnace further, it is very high temperature, the intensity of the blue radiation was large. That is why we saw this iron rod as blue. A black body is an ideal body, is an idealized body which absorbs, is an ideal body which absorbs radiations of all wavelengths, and it also emits radiations of all wavelengths. So, this is what black body is. It actually absorbs radiations of all wavelengths, it emits radiations of all wavelengths. Okay. So, there are many black experiments on this black body. So, let us draw a plot. So, in my x axis I am drawing wavelength lambda, in the y axis I am drawing intensity, call that I. So, which wavelength has how much of intensity? That is the radiation, that is the color of the radiation that we will see. When one does this experiment, one sees that a plot like this appears. What does this plot say? That this is an intensity versus wavelength plot. This says that at this plot was obtained at a particular temperature, let us call this temperature T1. This plot tells that at temperature T1, the intensity of light intensity of the radiation of wavelength lambda is this much. This is the intensity. As we increase the wavelength, the radiation, the intensity of this radiation increases, it increases up to this point. At a particular value of lambda, the intensity is highest. Let us call that as lambda max, and it is at a temperature T1. And afterwards, the intensity of this radiation keeps falling. This is what was experimentally observed. And when we say that a particular object appears red or blue or whichever color at a particular temperature, that means the lambda max corresponding to that temperature is that particular color. So, if the iron rod is red, that means lambda max corresponds to the wavelength of red color at that particular temperature. When you heat the substance further, so when you monitor the black body radiation at a higher temperature, this is what the plot looks like this. So, you see again the same story, the intensity of the wave intensity increases as the wavelength increases until one point, that again we call it lambda max, but this lambda max is at a different temperature, and then again the intensity falls. All right. So, you see that this is the curve that I am getting at temperature T2, which is higher. T2 is greater than T1, right. So, at a higher temperature I can see a different color because my lambda max is different. Lambda max corresponds to one particular color. All right. So, this is what experiments showed. If you use the wave nature of light and do a calculation without doing this experiment and try to explain the experimental result, this is what one obtained. This I am drawing in the blue color. This is what one was obtaining. This is the result from wave theory of light. If you use the wave theory of light, this is what your theoretical calculation gave. You know, it is very important to do these theoretical calculations, because every theoretical calculation invokes a certain understanding, it proposes a theory, it builds a fundamental hypothesis on the basis of which it explains its results. If that result does not match with accurately carried out experiment, it means that the hypothesis or the underlying assumption in the theory is perhaps wrong. So, therefore, that requires a revisit. So, this is what the wave theory of light gave us described, which agrees well at higher wavelength, but at lower wavelength or higher frequency the agreement is extremely poor. You can see that it could not correctly predict the intensity of the radiation of these wavelengths in this region. Right. So, this was a major problem. How did it get resolved? It got resolved by the work of a German scientist, Max Planck. What did he suggest? He said that, well, these black bodies are emitting radiation. He assumed, he made this assumption that, let us say that all molecules, they absorb or they emit radiations, but they do so in a particular way. They absorb or emit these radiations as packets of energy. In the wave theory, it said that when the light falls on a body, or when the body radiates light, it is a wave and it gets propagated. But Max Planck invoked one assumption that absorption or emission of radiation occurs as packets of energy. They are discrete, they are quantized packets, and these packets he called as, one packet is called quantum, and the plural is quanta. So, he said that molecules absorb or emit radiations as quanta. All right. So, what is, if this is some packet, what is the energy of that packet? the energy associated with that packet, remember this is a radiation, it has a certain frequency, it has a certain wavelength. The energy associated with this radiation, he said, depends on one constant, that is h, and the frequency of that radiation. He gave this famous equation E equals h nu, where nu is the frequency of radiation and energy E is the energy associated with this frequency, where this h is actually a proportionality constant that is known as Planck's constant. It has got a fixed value which is 6.626 into 10 to the power minus 34 joule a second. When Planck invoked these two postulates, these two hypotheses, he then redid the theoretical exercise, and his calculations correctly reproduce the experimental results. This way Max Planck suggested or proved that indeed molecules observe and emit radiations as packets of energy, because this hypothesis could explain the experimental results. All right. We will take one example. Let us say we have a radiation whose wavelength is 5000 angstrom, which is 5 into 10 to the power minus 7 meter. All right. Now, let us find out what is the energy associated with this radiation. We know energy is E is given as by h nu from Planck's theory. H is known, is a constant, nu is the frequency, but what I have is lambda, but I know how nu is related to lambda, that is C by lambda. So, now I have everything. H is a constant, 6.626 into 10 to the power minus 34 joule second, multiplied by C, which is 3 into 10 to the power 8 meter second inverse, divided by the wavelength, which is 5 into 10 to the power minus 7 meter. If you take this number 6.626, multiply it with 3 and divide it by 5, I got it as 3.97 into 10 to the power, the powers will collect now, is minus 34, this is plus 8, this is minus 7, when minus 7 goes up it becomes plus 7. So, it is plus 15 minus 34, it is 10 to the power minus 19. What is the unit? Meter, meter they cancel out, second inverse second they cancel out, I am left with this unit. So, the energy associated with the radiation 5000 angstrom is 3.97 into 10 to the power minus 19 joules, which is actually a very small amount of energy. So, the number has 10 to the power minus 19. Right. And this unit actually is not a very convenient unit to use, because you have to always tell 10 to the power minus 19 unit. We will convert this unit, we will use a new unit which is called as electron volt. It is written as small e capital V, electron V for volt. 1 eV is 1.6 into 10 to the power minus 19 joule. Now, if you try to convert this energy, which is 3.97 to 10 to the power minus 19 joule to electron volt unit, you would get energy as 3.97 into 10 to the power minus 19 divided by 1.6 into 10 to the power minus 19. The unit is in electron volt, and it comes out to be 2.48 electron volt, and you can see this number is easier to handle. So, often in these calculations in this field of study, one uses this electron volt unit for the convenience that I just established. We saw how we needed to invoke the particle nature of light to be able to describe the black body radiation problem. The other problem, the other experimental problem that required the invocation of particle nature of light is the famous photoelectric effect. What is this photoelectric effect? The experiment was carried out by Heinrich Hertz. This is, here I am showing the experimental setup. What you see here is a vacuum chamber. This is a vacuum chamber here. It has been fitted with one metal surface. it is a metal surface. You can take any metal, and the other side is again a metal detector. These two this metal surface and the metal detector are connected through each other by a potential difference. So, here is a battery that you see, this is the positive terminal, this is the negative terminal. Let me write that down. Positive terminal is the detector, negative terminal is the metal surface, this is the battery, and here I have got one ammeter. Let us put a needle in this ammeter. So, when there is a current flowing through this circuit, the ammeter will show how much of current. This is the experimental setup. What they did, what Heinrich Hertz did, was to shine radiation onto this metal surface. When he did that, when electromagnetic radiation fell on the metal surface, some interesting observations he made. First thing he saw is instant ejection of electrons. So, what he saw, when light fell on this metal surface, he saw that electrons came out of this metal surface and they started going along this direction. You see, electrons are negatively charged particle and here is a positive terminal. So, the electrons will go this way. That is why we have kept this particular polarity. So, what he saw is that when the light fell on this metal surface, instant ejection, this word instant plays an important role in this discussion. Instant ejection of electrons from this metal surface was seen. How did he say that? Because when electrons come from this side to this side, the ammeter actually shows that current is flowing. So, that is how he got that instant current flows. That's. The other thing is what he observed is that he changed the frequency. So, this he is shining the radiation, he played a bit with the frequency of the radiation. What he did, what he saw is that he started with very low frequency and then he saw there was no electron coming out. Then he increased the frequency slowly and then he saw that electron ejection, the ejection of electron starts only when the frequency is greater than a certain value of frequency. Let us call that nu 0 and he called that as a threshold frequency. Only when the frequency of radiation is above nu 0, that the threshold frequency, he could see the ejection of photoelectron. The photoelectrons are essentially the instant ejection of electrons from the metal surface upon shining of irradiation. All right. So, this is what he saw by changing the frequency. The other thing that he observed is that when he increased frequency, of course, after a certain value of frequency the photoelectrons are coming out, but when he increased the frequency even further, he saw that these electrons which are coming out of this photoelectron, they start moving faster and faster. So, the kinetic energy of electrons, the kinetic energy of the ejected electrons increases with frequency, with increasing frequency. So, as you increase the frequency, the kinetic energy of the ejected electron increases, but the current does not change. For a given value, when you change the frequency for a given intensity, the current value does not change. That means, number of electrons coming out remains the same, but the kinetic energy of these electrons are faster. Then he did something else. He said, okay, let us fix the intensity at a particular value, and that particular value he chose as greater than threshold frequency, and let us play with the intensity of the radiation. So, he took a particular value of frequency and he started shining the radiation of low intensity, that frequency light, then he increased the intensity of the light without changing the frequency, and then he observed the following. What he saw is that it does not matter what is the intensity of the radiation, as long as the frequency is greater than threshold frequency nu 0, he always saw the ejection of photoelectron. Even low intense radiation could eject photoelectron, right. But what he saw, by increasing the number of increasing the intensity, what he observed is that number of electrons, number of photoelectrons ejected from the metal surface increases with intensity. As you increase intensity, the number of photoelectrons that are coming out increases, but their kinetic energy does not change. They come out in more number, but they all travel in the same speed. Kinetic energy is unchanged. These are the observations that Heinrich Hertz's experiment showed. Now, up to at that point of time, if you use the idea that light is a wave, the energy of that light was believed to be coming from the intensity. If light is a wave, it could not be explained that why instant ejection of electrons occur, because if it is a wave, it hits the surface, it gets transmitted, and then it does its action. So, there has to be a time lag, but in this experiment there was no time lag, it happened instantly, as if it was showing as if light was not a wave, but it is actually a bullet which comes, hits the surface, kicks out the electron instantly. So, it was already indicating that wave nature of light is inadequate to describe photoelectric effect. The second thing is that intensity was, as I said, was believed to be the form of energy. So, higher intense light was believed to have higher energy. If that were the case, conservation of energy would have suggested that if you shine high intense light, which has now high energy according to that belief, it will come and kick out the electron. To kick out the electron, of course, you have to give some energy, because the electron is bound to the metal. So, to kick out that electron, you have to pay some amount of energy. The remaining amount of energy will be reflected as the kinetic energy of that electron. So, if you give high intense light, that should have shown that the electrons are actually moving, coming out, and they are moving much faster, because they have now got more kinetic energy. But that was not what observed in these experiments. On the contrary, what was observed is that when you increase the frequency, the kinetic energy of these ejected electrons increased. This indicated that the place or the frequency is the quantity which carries the energy of the light. So, these are the indications that were coming out of this photoelectric experiment, and it was successfully explained by Albert Einstein by making the following hypothesis. We will discuss what Einstein did to describe this effect. All right. Einstein said, okay, this is what we have to solve this instant ejection of electron. So, he assumed that, let us assume that light contains a beam of particles. Light is not a wave, he said no, light is not a wave, rather light contains a beam of particles, it is a series of bullets that are coming, and he called them as photons. One is photon, the plural is photons. It is exactly this in similar language that Max Planck said, and he called it quantum. Einstein now calls it photon. And he said, okay, this is the photon, the light contains a beam of particles which are photon, and each photon carries an energy. The energy of this photon is again following, it came out to be the same as Max Planck's. He said that the energy of this photon, which has a certain frequency, because it is a radiation, the energy of this photon is given by E equals h nu, where h is the Planck's constant and nu is the frequency of this light that is coming. Then he said, okay, how about intensity? The intensity of a light does not reflect its energy, rather it reflects number of photons in the light. So, the frequency corresponded to the energy of the light, the intensity corresponded to the number of photons of each photon carried the same energy E, number of photons in that light present is given by the intensity. This is what his assumption. With these three assumptions, he could explain everything. Now, why do you see instant ejection of electrons? Because light contains a beam of particles. So, it works like a bullet. The light comes as a bullet, as a particle, it hits the metal surface, kicks out the electron, and it happens instantly. There is no problem. So, this observation could be explained. The second observation can be explained if we say the energy frequency corresponds to energy. So, now it said that okay, that makes sense, because at a lower frequency we could not see the photoelectron coming out. It required a threshold value of frequency. So, beyond that frequency, that means beyond that energy, all radiations of higher frequency can do this photoelectron, can eject photoelectrons, because they have sufficient energy to do it, because you need to give a certain threshold value of energy to the metal to be able to remove that electron, because the electron is bound to the metal. You have to give that energy. We will come to that. And then again, when he said that okay, you keep on increasing the frequency, so what happens? There is a conservation of energy. So, this is what is the next, the conservation of energy. He said h nu is your h nu 0 plus half mv square. Nu is the frequency of the light that is getting irradiated. The energy corresponding to that light is E. Nu 0 is the threshold frequency starting from which you see photoelectrons. So, this is the energy that you have to give to the metal in order to be able to take that electron out. So, this is the binding energy of that electron to the metal. So, this is called as phi, given as phi, and called as work function. Different metals have different work functions, because you need to pay different amount of energy to remove their electrons. And the remaining amount of energy, so the radiation brought energy E, and it had to pay phi or h nu 0 as the work function of that metal, that is the minimum energy that you have to be able to eject the electron. The remaining energy is reflected as the kinetic energy, half mv square of these ejected electrons. So, when you increase the frequency here, the kinetic energy increases. Of course, when you increase the frequency, this is a constant for a given metal. So, the remaining amount of energy, that is h nu minus h nu 0, is reflected as half mv square. So, mass is a constant for electron. So, there the remaining term is v. So, the speed increases. And what happens to the intensity story? The experiment showed that when you have more intensity, with increasing intensity, you have the same kinetic energy, but more and more photoelectrons come out. That also can be explained by this hypothesis, that intensity corresponds to number of photons in light. When you are using a high intense radiation, you essentially are sending more and more photons of that energy. And since more and more photons are coming, each photon, now it is a particle, each photon hits the surface, kicks out one electron. So, you have more and more number of photons. So, you can see ejection of more and more number of electrons from this metal surface. So, in this way Einstein could explain the photoelectric effect, but to be able to do that, he had to invoke the particle nature of light. So, we saw light had particle nature from photoelectric effect, from black body radiation, but light also had wave like nature, because it shows diffraction, it shows interference. So, at the end of the story, it was very difficult for scientists to believe at that point of time, but this is now well established that light possesses dual behavior. It shows wave like nature, it shows particle like nature, depending on the experiment that we are carrying out. So far we have seen that there are two sets of experiments, namely the black body radiation experiments and the photoelectric effect experiments. These two experiments showed some results which could not be explained with the wave theory of light. That required, in case of black body radiation, the effort of Max Planck, and in case of photoelectric effects, the efforts of Albert Einstein. These two scientists, they invoked the particle nature of light and could explain the experimental results that were coming out from black body radiations and photoelectric effect. Now, we will discuss another set of experiments which could not be explained by using the wave theory of light. This set of experiments are called, we will call them, they are from atomic spectra. The atomic spectra that were obtained for various atoms, they showed some results, we will discuss those results, which could not be discussed or which could not be described in terms of the wave theory of light. Before we go to the atomic spectra and how they were so difficult to be described, let us discuss what is this spectra, how does one get them. These atomic spectra, they are obtained from these sets of experiment that are called spectroscopy. It is a very useful branch of science using which one obtains the structural information about matter. This branch of science essentially deals with the interaction of radiation with matter. By matter I mean it could be atoms, molecules, ions. So, it says how light interacts with these matters, and from there what structural information can we obtain about the matter that we are studying. And from this structural information, of course, we can go and discuss about their property. So, therefore, spectroscopy is a very important branch of science. Let us begin our discussion by the electromagnetic spectrum that we already have seen. If you remember, electromagnetic spectrum consists of a series of electromagnetic radiations that differ, those differ in terms of their frequencies. In this case, we discussed already that the frequency range from 10 to the power 24 to 10 to the power 0, and the wave numbers correspondingly change. If you remember, we also discussed about this important region, that is the visible spectrum. These are the wave numbers, these are the wavelengths that our eyes can perceive. We call them visible spectrum. They range from 400 to 750 nanometers, and you can see a continuous series of colors starting from violet, indigo, blue, green, yellow, orange, red. You see a continuous spectrum of colors in between 400 to 750 nanometers, and they constitute the so called visible spectrum. We also discussed that electromagnetic radiation, they do not require a medium to travel. In vacuum, all electromagnetic radiations travel with the same speed, that is the speed of light, which is 3 into 10 to the power 8 meter per second. However, when these electromagnetic radiation are passed through a medium, they show different speeds. They show different speeds with respect to their wavelengths. Different wavelengths behave differently in different media. You might have done this experiment as a hobby experiment. When we pass sunlight, just ordinary white light, through a prism, the prism actually splits the white light into the 7 continuous colors that you can see here, the rainbow colors starting from violet till red. The incident radiation was white light. The prism converted this white light into series of this visible colors. Why did that happen? Because when the radiation goes through the prism, the prism offers a different medium. In this medium, different wavelengths, that is the blue wavelength, green wavelength, yellow, orange, red, these different wavelengths, they get deflected from their original path by a different magnitude. The lower wavelength, the colors with lower wavelength get deflected or they get bent by a greater magnitude than the colors of higher wavelength. That is why the prism can split the incident white light to a series of continuous colors from violet to red. But in our discussion, we will talk about two different forms of spectroscopy. One is what we call absorption spectra, two emission spectrum. What happens, what do we mean by absorption spectrum or emission spectrum? Let us redo this experiment, the splitting of white light into the rainbow colors, but in a slightly different manner. Let us say that before I shine this, before I allow this white radiation to go through the prism, I did something else. So, I started with white light, I passed this white light through what I call my sample. It could be the atom that you are studying, it could be a molecule, it could be an ion. So, this is the sample, this is let us say a certain molecule or an atom. So, we passed first the white radiation through the sample, and then we took the light that is coming out of the sample and then allowed that light to pass through the prism. When we did that, you see that the prism again splits the white light into several colors, but if you compare this spectrum with this spectrum, the one thing that you would notice is that the yellow color that is present here is missing. Something has happened here. Instead of yellow, I see a dark patch. I see red, I see orange, I see green, blue, indigo, violet, but I do not see yellow. What happened to that yellow color? What has happened is that the sample that I have, the molecule or the atom that I have in this sample, they have actually absorbed this yellow light. So, the white light came, the sample absorbed that yellow light from this white light. White light has the wavelengths of all these 7 colors, but the sample could only absorb the yellow light for whatever reason. This is just an illustrative example. The sample absorbed the yellow light, and the remaining light, when they were passed through the prism, all the lights were present, but except for this yellow light. So, what has happened to this yellow light? The yellow light has been absorbed by this sample. So, what I get now, this spectrum, this is the regular spectrum that I get by passing ordinary white light through a prism, and now this is a new spectrum which I call absorption spectrum. Why absorption? Because my sample has absorbed one color and the spectrum does not show that particular color. Okay. Now, this is what we mean by absorption spectrum. There could be another possibility, that is this next type of spectrum, that is emission spectrum. Let us keep the absorption spectrum here. How do I get emission spectrum? Now, to be able to get emission spectrum, we have to do a few other things. When would a molecule or a matter emit radiation? When we were discussing black body radiation, we saw that when we heat, let us say when we heat an iron rod in a furnace, at different temperature we see a different color of the iron rod. At one temperature it was red, bright red, another temperature at even higher temperature it was blue. That is because when we heat the substance absorbs a lot of energy and it does not feel happy there. So, it starts irradiating energy in form of radiation. This is exactly what we are going to do in terms of spectroscopy. What we will do is that we will take our sample, but we will excite this sample. How can we excite the sample? We can simply heat it, that is a form of excitation. We can also pass light through it, that is also a form of excitation, because light contains energy. Or we can also put this sample in a electric discharge tube. You remember those cathode rays were going through. So, if we apply very high voltage, lot of electrons will be produced between the cathode and anode, and these electrons will hit the sample, and then the sample will get excited. It will absorb a lot of energy, and then it will get excited. And once the sample is excited, it has got a lot of energy, but it does not know what to do with this energy. So, what it essentially does is it emits this extra energy. This is what we are going to discuss next. Here you see I have prepared an excited the sample in an excited state. So, I have done something, either I have given irradiation, or I have heated it up, or I have subjected it to discharge tubes, electric discharge tubes. In any case, I have this excited state sample which has absorbed some energy, and when I allow it to relax, it emits those radiation. When I take this radiation, but remember, in previous experiments these arrows meant ordinary white light. In this experiment, the arrow, that is the light that I am passing through the prism, is the irradiation that is coming from the excited sample. So, when I allow this radiation to go through the prism again splits them, but in this case the sample had, in my previous experiment, the sample had absorbed this color, and in this experiment after when I allowed the sample to relax, the sample has emitted the yellow color, and this yellow color comes out of the prism. So, what we see here in this second experiment, we call that as emission spectra. In the absorption spectrum, we saw all the lights except the light that was absorbed. In the emission spectrum, we saw only the light that was emitted. This is the basic difference between absorption and emission spectrum. Now, this emission spectrum is a very important tool to identify atoms. In fact, it is called, it can be, every atom produces a unique, a signature emission spectrum. This can be used for fingerprinting the element. Using the atomic emission spectrum, several new elements have been discovered. Even the presence of helium in the sun was discovered or was established by analyzing the emission spectrum of helium atom. Since the emission spectrum carries signature properties of an atom, we will now discuss how does the emission spectrum of hydrogen atom look like. We call that as line spectrum of hydrogen. We will get to know in a minute's time why we call it line spectrum. It is essentially a form of emission spectrum. This is how the emission spectrum of hydrogen looked like when scientists carried out these experiments. What you see here in a typical line spectrum of hydrogen atom, you see series of lines, and then you see at different intervals some bands that you see. There are some bands, then there are some lines, then there are bands, then there are again some lines, again some bands. I have intentionally colored them so that we can see that here is a group, here is another group, here is another group, and they appear at different wave numbers. So, you can see that they go from 91.2 nanometer to more than 820 and above, right. So, there are this series of there are various groups of lines that we see, and this is why we call them line spectrum of hydrogen. Okay. If you look these lines which are shown in yellow color, they come between 364 nanometer to 656 nanometer. That is the normal visible range of the electromagnetic spectrum. So, when scientists recorded this emission spectrum of hydrogen atom, they had no clue about what is happening. Why are these lines and then there are bands? So, they were completely clueless. There was no theory available which could explain why such a spectrum should appear for hydrogen atom, which is extremely simple. And again, for all heavier elements, helium, lithium, they also their emission spectra were also recorded, and their spectra also showed somewhat similar structures, but they were even more complicated. We will now focus on this region, which is shown in the yellow color, which comes in within the visible range of electromagnetic spectrum. So, I have now zoomed this region. So, let me turn this. So, this spectrum ranges from 364 to 656 nanometer. And if you see carefully, again the same thing that appears in the previous spectrum. There is one line here, there is another line here, then one more line which is closer, and then you can see that the spacing between the lines keep on decreasing as we go lower wavelength. And finally, you see a continuous band. It is a very wide band. So, as if several lines are all appearing together. So, they have given rise to a band. Now, this was very puzzling, but one mathematician, Swiss mathematician, his name was Johann Balmer. In the year of 1885, this Swiss mathematician, he was not a professional spectroscopist, but he tried to understand these lines that were coming at different numbers, and he said, all right, let me see if I can fit these numbers to an analytical formula which can explain why we are getting all these bands. So, he suggested a formula which is called Balmer's formula, as nu bar, which is the wave number, as this very strange number, he said that these lines that you are seeing in the hydrogen atom emission spectrum, they can be explained with this equation, where he has a number here 109677, then there is another number 1 over 4, and then here is 1 over n square, where he said that n can be 3, 4, 5, it goes on. So, it is essentially n has to be greater than 2, because if n is 2, then this term becomes 0 and the wave number disappears, it becomes 0. If you look at this equation, let us see when n is 3, what do we have? The nu bar will be 109677 I will do it for one case, 1 by 4 minus 1 by 9. And this number is in the units of centimeter inverse. If you if you solve it, you would get 15,232 centimeter inverse, which is equivalent to 656.5 nanometer. So, when you plug n equals 4, the nu bar comes out to be, I am writing here, 20,564 wave numbers, which is 486.3 nanometer. And if I show you the spectrum again, you can see the first line appears at 656, the second line appears at 486.3, and then if you use this formula, you will get the numbers that where these new lines, other lines should come. Where will this formula end? If you see this term n, if n is very large, here you have only 1 by 4, if n is very large, so this second term will become close to 0. So, we have when n is very large, we have essentially 109677 divided by 4 wave numbers. This 4 is coming from here, which is 27,419 centimeter inverse, or equivalent to 364.7 nanometer. And this is where you actually see this continuum band, 364.7. So, when n is very large number, let us say n is 100, then you would get 364.7. When n is goes from 100 to 101, the change in the nu bar will be very small. So, therefore, the lines will be extremely closely spaced and they will appear to form a continuous band. This is what he said. So, using this formula, he could actually explain this series. Remember, this series is only one part of the entire hydrogen atom spectrum. I started to analyze these yellow lines. This is the complete spectrum and this is the zoomed out version of the visible range. So, let us go back to the complete spectrum. This is actually not complete. There are again many lines towards the right hand side. So, these lines that are there in the yellow color, they could be explained by Swiss scientist Johann Balmer. So, therefore, we call these lines as Balmer series. Okay. Following the work of Balmer, there are other scientists who could see that they can also explain the remaining part of the hydrogen atom spectrum. For example, this part, this region could be solved by Lyman. So, we call this as Lyman series. The equation that Lyman used was very similar to the equation that Balmer used. He used nu bar is 109677, the same number, multiplied by 1 divided by 1 square minus 1 by 1 n square, and the number is centimeter inverse. And in this case, n goes from 2 to 2, 3, 4 and so on. If you compare this, the first line with the first equation with the second equation, you can see the second equation is actually the equation given by Balmer. So, the first equation that you see here was given by Lyman. So, we call the lines that were described because of this equation as Lyman series. This was due to Balmer, and then you can see a trend. So, here n remains same, 1 square, 2 square, 3 square, 4 square, 5 square and so on. Then this was given by Paschen, Brackett, Pfund. These are various scientists who used different forms of equations to explain this hydrogen atom emission spectrum. So, we call this the numbers that are coming from this equation Lyman series, Balmer series, Paschen series, Brackett series, Pfund series, right. So, you can see we have a series of equations now, but there are some similarities. The similarities, if you see, is that we always have this n over here, and then the term that is present here, it keeps on increasing 1, 2, 3, 4, 5. Then there was this Swedish scientist Rydberg, who saw the pattern here and said, we do not have to use all these equations, we can generalize them. He generalized them in this way. He said that, okay, let us use the same. He made it 1 minus n 1 by n 1 square minus 1 by n 2 square, and these numbers are in centimeter inverse, where his only precondition was there that n 1 is anyway again integer 1, 2, 3 it goes on, n 2 is always greater than n 1. If you use this formula, you can actually reproduce Lyman series, Lyman formula, if you put n1 is 1, if you put n1 is 2, you can reproduce Balmer, n1 is 3, you can reproduce Bastian, and so on and so forth. And this number that was used by everyone, we call that as Rydberg's constant, or we denote it as RH. Although Rydberg's formula could reproduce the lines present in the hydrogen atom's emission spectrum, what was not clear is that what are the physical significance behind the uses of this n1 and n2. It was very puzzling to see that these integer numbers are used in this relation, because we always thought that we human beings invented numbers. We invented numbers because we needed them for counting. What these numbers n1 and n2 are doing in this relation was not clear. So, although Rydberg's formula can explain the hydrogen atom's emission spectrum, but it is merely an equation that reproduces some lines, nothing more than that. We needed a physical interpretation that would give us a physical idea about what is happening in hydrogen atom. And this is what we are going to discuss next. We will talk about the idea of Niels Bohr, and we will talk about Bohr's atomic model and how Bohr's atomic model could explain the complicated emission spectrum of hydrogen atom. This is what we are going to do in the next class. Thank you.